we have, again, from Princeton, we've got Ilia Kochergin talking about Schwinger model on the lightcone.
Yeah. All right. So first of all, thanks to the organizers for inviting me to give this talk. I'm going to talk about Schwinger model on the lightcone, and this is based on the work in progress with several people from Princeton who are all in this room as well. So let's get started. The discretized lightcone quantization, or DLCQ, is a method introduced in the 80s to study 2D gauge theories. And the idea is to quantize the theory in lightcone coordinates using x plus as time variable and impose the lightcone gauge. Then we can integrate out the gauge field and one of the permanent components. And for example, for the multi-flavor Schwinger model with equal masses, we get the following Hamiltonian. So we have one component permanent fields psi I with non-local interaction. Then at this point, there are many lightcone-based approaches that use some set of continuous basis functions to study this Hamiltonian, but in the DLCQ, we instead compactify the special direction on the circle, and because of that, the momentum becomes quantized, and on the lightcone, the fermionic momentum should be strictly positive, so there is a finite number of states with the fixed total momentum number k, and the infinite volume limit is recovered by taking k to infinity. Well, one issue with all this story is that it is impossible, or at least very hard, to study states with non-trivial topological structures. So we can only take the term equal to 0. But on the other hand, this gives us a continuum theory, and we only need to take one infinite volume limit. We also can explicitly see the permanent quantity of states and do a Barton number truncation, for example, if necessary, to speed up the computations. And specifically in this Q, the matrix elements are quite easy to compute. But there is still one problem associated with boundary behavior. This is probably why the DLCQ became much less popular like 20 years ago. If we restrict the Hamiltonian to permanent sector, then in the infinite volume, the bound states have this form where B dagger and B dagger are permanent and other permanent creation operators, and this phi is the wave function that defines the momentum distribution between them, and this satisfies the Koch equation where this extra term also appears for singles. So for this equation, we know that this phi has power-like behavior at the endpoints, and we can exactly find this power beta. And in the strong coupling regime and goes to 0, this beta also becomes very small. So it is very hard to study this regime by using discretization. Van de Sande studied this problem, and he found that the DLCQ converges as 1 over k to the power of 2 beta, which is very bad, as evidenced by this plot. So here is the exact result, and here we have the DLCQ results. So one way to improve that is to use some basis of continuous functions that incorporate this kind of behavior as it was done for lightcone conformal truncation, for example. But Van de Sande also proposed to modify the Hamiltonian by modifying this principal value term and then discretizing. And this also works quite well. And a similar thing can be implemented for the full Hamiltonian as well. But there is still one caveat, is that this power beta is actually renormalized by terms with high fermion number. And in the past, some of the work didn't take that into account, so there are some discrepancies. And that also means that we have to somehow find beta. A possible way to do that is to try to minimize the ground state mass with respect to beta. And this works for basis function methods. But in the DLCQ, it just gives beta equals to 0. So instead of that, we try to optimize the convergence of this mass that is given by this derivative. And as k is discrete, we need to take a finite difference approximation to this derivative. Now, this plot shows that this actually works quite well. Here we have the exact results. That's infinite k for this is all for the two fermion sector. And in the wide range of case, the DSQ results can be fitted by a simple power law. So with this, we have a method to find betas. So now let's get to the results. First, for the two-flavor model, we know that in the strong coupling regime, and yeah, I didn't mention that, but I set the coupling to square root of pi. So this mass is the units of coupling times square root of pi. So, and this theory has an effective description in terms of sign-Gordon Lagrangian, and because of that, we know that there are two bound states, the adjoint pi's and singlet sigma. We also know exactly the mass of pi because sign-Gordon is solvable, and the mass ratio of sigma and pi in the limit when n goes to 0. And both of these results are quite well reproduced by the numerics, as on these plots, these numbers. But you can see that even at quite small m, the numerics already start to differ from the leading order approximation, and we need to include higher order corrections to the PT. So then we move to the two-flavor model, to the three-flavor model, and this is quite uncharted territory. The three-flavor model, as you know from theory, is described by perturbed S3WZW model, and we can only say something about how the ground state mass scale with quark mass, and this scaling is reproduced by the numerics. And we can also find the strong coupling regime bound states. So now there are actually 3 adjoint states, including the adjoint ground state, and there is one adjoint state very close to the threshold. This plot shows the ratios of bound state masses squared to the ground state mass squared, and there is also one singlet. So finally, we move to the four-flavor model. This is perturbed SU4WZW. Once again, we only know the scaling, which is quite well reproduced by the numerics. And as for the state content, there are again 3 adjoint states, including the ground state, a singlet state, and besides that, there is a quite peculiar state in 20 prime representation of SU4. And it is interesting because this state in 20 prime has exactly 0 to fermion part, and also its mass ratio actually increases with fermion mass, unlike all the other states. So, yeah, this is all I want to say so far. I'll just say some things about possible future directions. So the main point of all of this is that DLCQ can actually be used in the strong coupling regime, just like many other methods. And potentially we can increase precision of our calculations even more by using high case. We can do more calculations for different numbers of flavors and try to compute other observers like some correlators. And we can also try to study UCD instead of QED, like, for example, it was in Benstock. So, yeah, this is all I wanted to say. So now I'll be happy to answer the questions. Bye-bye. Yeah.
Can you say a little about the fermion content of this 20 prime state? I can't figure out the uncomfortable.
Oh yeah, the 20 prime, it has 0 to fermion part, so it starts with like 2 meson for fermion.
Okay.
Yeah, and but it is mostly for fermion, but then there is a small 6 fermion part as well.
Okay, yeah.
Yeah. So yeah, it's like purely a tetrapore.
And decay.
No, it's a bound state. So all the states that I've talked about are bound states. So it is quite close to the threshold. The ratio of mass squared is 3.76, but it's still less than 4. So.
as you increase the fermion mass,
Yeah,
does it ever cross threshold?
well, I think, yeah, I didn't check for a larger M because it takes some time to do calculations, but yeah, I think it probably becomes heavier in the big category when M is much larger than one. Yeah.
Like, is it often, we need to, like, whether it's possible to add a plate?
Well, I tried to think about that, and there are some papers how to do it on the lightcone, but well, what I certainly know is that it would be more complicated than this. We have to use some like more complicated wave functions, but I haven't thought about that in details.
Like, say, okay, so forget about like convergence or whatever, it's like a piece in the base, and just like Hamiltonian, is it obvious, like how to write them in my.
Yeah, so if you try to naively write it in lightcone, it would be quite meaningless. So you need to, yeah, you need to somehow consider more complicated states. So states, basically, I think the idea is that, so I'm using the lightcone gauge here, but sorry, yeah, I'm using the lightcone gauge A minus equals to 0, but I think the idea for non-trivial theta is use A minus equals to 0 for non-zero modes and A plus equals to 0 for 0 modes. Then we have A minus for 0 modes, and we can consider like some winding and use winding states to construct theta vector, but it would be quite complicated. There will be some like wave function for those zero modes. But like I said, I haven't thought about that in details, so
Yeah.
I don't know much yet. Yeah.
We're question about this function prime, so is it submitted carrying two places the same or something, or not an accident?
I think it's an accident, so it's certainly like it appears in the product of symmetric product of two adjoints, so potentially it could decay.
It could have decayed.
Yeah, it could have decayed, but yeah, it just happens to be below threshold.
So if we imagine recurring this model by some other stuff, then before we operator. In principle, as you vary other parameters, it might be able.
Yeah, like, yeah, it can be pushed above the threshold by something, yeah.
Good. There are no more questions. Thank you again.
Right.